Alrighty, guys, can you hear me? Are there any questions? Okay, then we'll give it a few more minutes and then we'll get started. Okay, I think it's time to get started. Can you guys hear me?
Yes.
All right. So switch over to document camera. There you go. So there are no office hours this week, and this is because of Thanksgiving. So that's one thing to note. The other note is to check the exam schedule on Canvas. So let me know of changes. And if you haven't asked me for a time slot, let me know of your wish for a time slot. This is if you haven't. Already. But have a quick look at the schedule. Make sure that that your name appears where it should, and if it doesn't, let me know, and we try to fix it. Okay, so so tonight we're going to do one more example on either. I should say here that there is an additional set of practice problems posted. So if you want to practice more on Ethos Lemma, go to Canvas and grab that set. And so we're going to do one more, and then the big theme of tonight is going to be a change of measure. And in continuous time with Brownian motion, this is called Kirsanov's theorem. So we're going to be looking at that this week. We'll start tonight and we'll continue on Thursday. No, not on Thursday. We'll continue next Tuesday. Okay, so we'll do one more example and then we'll switch to talk about changes of measure. We already talked a lot about change of measure in discrete time and random derivatives in general. So now we're going to be looking at change of measures in continuous time. Okay, so let's do one more example using Ethos Lemma. So we're going to look at this square root process. We also had that one last time. So we're going to look at dRt is equal to a minus bRt dt, and then sigma square root of rt dbt. So we could be interested in, so this is an SDE because, well, R appears both on the left-hand side and on the right-hand side. We're going to have an initial point that is positive. Right, so remember, this is by definition. This is nothing else. This is just notation for writing RT as R0 plus an integral from 0 to t a minus BRU du plus 0 to t of sigma square root RU dBU. These two things, they mean exactly the same. There's no difference. It's just much easier to write the top part than to write the bottom part. Right, so this is an SCE because R is here, R is there, and R is also over here. So we could ask questions like, what is RT's distribution? It's a random variable. What's the distribution? So that would be one question. Another question is, maybe we could ask just, so what about the mean and the variance? So R here is not going to be normal. And you can see that because this is not normal. And you can see that because if you look at the top equation, so you started out somewhere positive, and then you look at it. What happens when you get down to 0? If it ever gets down to 0. If it gets down to 0, right, then B here times R, this is going to vanish. And this term over here is going to vanish. That leaves it with A times dt. Right, so if it gets down to 0, that term drops and that term drops. And that means that the change in R is just going to be A dt. So for example, if A is positive, that means that the change in R when it gets down to 0 is going to be positive. So then it comes back up. And that means that R is positive. Every time it gets down to 0, these terms that involve R, they drop out, and I'm left with A dt. So if A is positive, it shoots back up. Right, so I have RT is then non-negative, and then it cannot be normal. So whatever distribution it has, it's not going to be normal. Mean and variance. Okay, so that's what we'll settle on tonight. And so this is what we'll do today, and then maybe later we can try to rethink about R's distribution. And so to do the mean, then let's just take expectation through. E of RT is equal to, well, R0 plus, and then an integral from 0 to t of A minus BE of RU dt, plus the expectation of the stochastic integral. And what's the expectation of the stochastic integral? What's the expectation of the stochastic integral?
Are we trying to do like an Ito isometry thing here or something else?
The Ito isometry, then we have to have a square here. There's no square. So what is the expectation of a stochastic integral? U here. What are some of the main properties of a stochastic integral?
Is it a martingale?
Yeah. So what's the expectation?
Is it 0 if it's a martingale?
Right, because if I put in a t equals 0 here, I'm going to get a 0. So that's 0. So now you see you have expectation of RT here, you have expectation of RU here. So if you define f of t just to be the expectation of RT, and then if you compute f prime of t, what are you going to get? Well, you'll take the derivative here. This will be a minus b f of t. And if I take f of 0, I'm just going to get R0. So this is a linear ODE, which you can solve. Remember how to solve linear ODEs? You have to get rid of this term here on the right-hand side. And the way you do that is by looking at f tilde t. It's going to be e to the bt times f of t. And then we compute the derivative of f tilde. This is going to be e to the bt times, then use the product rule. There's nothing random about f tilde, so we are just going to use the old product rule. So it's going to be b f of t plus f prime of t. And then you look at the form over here. So it's going to be a e bt times a. So now there's no f tilde on the right-hand side. There's no f on the right-hand side. You can now write f tilde as the initial point plus the integral. The initial point, this is the same thing as f0, because when you put in a 0 for t here, this is just going to be 1. You're going to get r0 plus, and then the integral of f prime, that was this guy over here. This was a e to the bu du. And that's something we can compute. This is r0 plus, and then we get a over b times e b t minus 1. And this one here was, this was EBTF. So now we have a formula for what f is. This is the same as saying that f of t is equal to e to the minus bt r0 plus a over b 1 minus e to the minus bt. So that's the mean. That was the mean. So remember, when you get something that has an affine structure like this one, you get rid of this b here by multiplying onto this exponential factor. And then by multiplying onto that, you compute the derivative. There's nothing that involves f anymore, and then you just get f tilde simply by integrating. Okay, so this did not involve Ito. So let's do the variance. This was the mean, let's do the variance. And so to do the variance, this is where we apply Ito. Apply Ito for the function x squared. So let's look at h of x being x squared, then we need the derivatives. H prime of x is 2x, and I need x double prime of x, which is then 2. I need these derivatives to apply Ito's lemma. And then Ito will say that the dynamics of h of RT will just be, so this is where Ito comes in. This will be h prime applied to RT, dRT. And then we always, whenever we have a Brownian motion, we always need the second order terms. This is going to be 1/2 h double prime of RT, and then you need the quadratic variation of R. All right, so this is Ito. Always remember this term. So we need to look at DRT to figure out what the dynamics are. We need DRT here, and we need the credit variation over here. So DRT, well, we have it right here. So we can start by plugging him in. So what is H prime? H prime was 2x. This is going to give me 2 RT. And then here comes the dynamics of R. This is A minus B RT. dt plus sigma root RT dBT. Right, so H prime evaluated RT. This is going to give me 2 RT. That's the first part. And then DRT is what comes here. And then I need the higher order term. I need 1/2 times H double prime. That was 2. And then I need the credit variation of R. Credit variation of R, there are 2 components. There's a DT term that does not have credit variation in it. It's only the Brownian motion term that has credit variation in it. And the credit variation of the stochastic integral, the way you compute it, is that you square the integrand. So this is going to give me sigma squared times R. And then instead of Brownian motion, you're going to get the credit variation of the Brownian motion, which is time dt. So you're going to be left over here with sigma squared RT dt. So it's a long mess, but at least you see this 1/2 times 2. This is going to give me a 1. And then I can collect the terms. I can collect the dt terms, and I can collect the Brownian motion terms. Let me do that. So I'll get RT outside, and then what will I get? Here would be 2a minus 2b RT plus sigma squared RT. And then I'll have my dt. So that's the drift. So you see it's a drift. And then I'll have the volatility. It's going to be 2r times sigma. So this is going to be 2 sigma r times square root of r. This is going to be RT to the 3/2 dBT. This is the drift. This is the drift term. This here is the volatility. Volatility term. So you have this decomposition in terms of a dt term and a dB term. And of course, h here, this was d of RT squared, right? So it's very similar to the situation we had before. We have the dynamics written out in terms of a drift term. So again, this here is drift. And this here, this is volatility. And so instead of writing it out as in this d form, I can write it out in integral form. Okay, so let me write it out in integral form. Write it out in integral form, I'll get RT squared is equal to the initial value, R0 squared. And then the 2 integrals, there will be a dt integral and a Brownian motion integral. So I have to integrate all this up. This is 2a plus sigma squared minus 2b u du plus an integral from 0 to t sigma ru to the 3/2 dbu. So I did nothing else. I just wrote it out in integral form. So what did we do before was we took expectation. So let's take the expectation. So let's take the expectation. This is the initial value squared, and then I'll have something in here that'll be an integral from 0 to t, and then I'll have an expectation of ru times 2a plus sigma squared minus 2b, and then an expectation of ru squared du. And what about the Brownian motion term? What happens to that one when I take expectation? What is the expectation of the Brownian motion term? Cn is right. This is equal to 0 because the stochastic integral is a martingale. Very good. And so we close, right? We're basically in the same situation that we were in before. We were hunting the mean. I called the mean for f, so let me call the second moment for g. So let me call the second moment for g. Then I'll get my ODE. This term here is what I call, this was my f of u from before. F of u from before, it was this one here. Right now here, this was equal to e to the minus bu r0 plus a over b 1 minus e to the minus bu. That was what we did from before. So if I have my function g here, I'll get the g prime of t. Take the derivative. The derivative will give me f of t 2a plus sigma squared minus 2b, and then it'll be g of t. And the initial value will be r0 squared. How would I go about solving this one? How would I solve something like this?
Can we try the same thing we did before?
Okay, so let's do g tilde of t. How would you define it? You need to get rid of
e to the that term.
It's always with a minus.
Yeah, the coefficient of
This guy times g. I'm going to try it out. What is g prime? G tilde prime. There's always going to be this exponential sitting outside. And then what's going to come inside? It'll be this coefficient with a minus sign times g of t plus, and then it's g prime. So this is equal to, and now we see the magic thing that happens. This is why the minus sign is important. Had you put a plus here, you wouldn't cancel out. This is minus sigma squared minus 2b t, and then you look at the form, you cancel out. I'm left here with 2a f of t. And then we just proceed as before. You integrate up. You're going to say that g tilde of t is going to be equal to the initial value. This is g0. And then you integrate up the derivative, g tilde prime of u du. And now you have a nice expression for that, which does not involve g at all. So the initial value for g, that was r0 squared. And in the integral that you just computed, this was 2a f of u e to the minus sigma squared minus 2b times u du. That's your g function.
I have a question.
Yeah.
So since we have oh, never mind. I was gonna say, since we have an integral and a derivative, couldn't we use like the fundamental theorem of calculus to make it tilde gt? But then it doesn't. That just, you subtract it on the other side and just get a true statement.
But that's exactly what we're using here, right? I can express g tilde as its initial value plus its integral of its derivative.
Okay.
Right? That's exactly what I'm using here, right? I'm writing g at time t is equal to the initial value, that's the bottom part, right? And then I integrate up the derivative.
Gotcha. Okay.
Other questions or comments? So we were able to compute. We were able to compute the first two moments. We still don't know what the distribution is. We'll save that. We'll save that for another day. We'll save that for another day. Or do you guys want to see how to compute the distribution? You guys say.
Yeah. Let's see.
You want to see it? Okay. Okay. So how would one go about computing the distribution? I think we did a lot of it last time. So we'll go have a look at the characteristic function. We'll have a look at the characteristic function. So what's the characteristic function? So now we have to look at the expectation of an exponential of I, and then you need the variable, we call it psi times RT. So please note here that this is an example where, so you could also, and this is what the textbook favors, Steve, he loves the moment generating function. But this here actually turns out to be an example where it's a bad idea to use the moment generating function. Because if I were to look at the moment generating function, right? So this here is a psi that's being mapped into this expectation, and this is our R over here. The same thing is true here, right? This is your psi that's being mapped into this expectation. But the problem is that this thing here is a number between 0 and infinity. And in this case, this is included. Whereas when you do this thing up here, this is a number. This is a number. This is never plus infinity. Because when you take absolute value, you're going to get something that is bounded by 1. But it's a complex number, right? This thing here is something that is valued in the complex plane. So how would one compute this? Well, so remember last time we were trying to compute these zero coupon bonds. So why don't we try to use some of that material and see if we can use this material to compute what this guy is. So like last time, so I should say similar to last time when we looked at the zero coupon bonds. We introduced a martingale, and the martingale is this MT. I shouldn't call it T now because T is fixed, so let me call it MU. So it's E, and then it's I, the variable psi, RT given, and then it's FU. We had something quite similar to this last time. And the thing to note is that there's a time variable here. So this is my U. U runs between 0 and T. And some things to note is if I look at M at time T, so I look at the upper limit, well, then I'll get E to the I psi RT.
Professor, what does that say similar to last time in the parentheses?
Zero coupon bond.
Oh, okay, gotcha. It's abbreviation.
Zero coupon bond. We did a calculation that was very similar to the one we're about to do now. So if I look at U at the upper limit, so U is equal to T, then I'll condition here on FT, and then what I have inside is measurable, and I'm just going to get the integrand back here. And then if I look at M0 on the other hand, M0 on the other hand is this expectation. Right, and that's the one I want. M0 is the thing that I'm looking for. This is our goal. Right. So if I can figure out what M is, then this here is just a comment. If I can figure out what M here is, if I can find a formula for M, well then I can evaluate that formula for U equal to 0, and it'll give me exactly what I want. Okay, so how would we do that? Well, let's try. So we want to come up with a guess. So just mathematicians typically call that for a conjecture. The fancy mathematician calls this for an ansatz. I call it a guess. Let's come up with a guess and then verify. Kind of an old way of doing math. You come up with a qualified guess and then you check that the guess works. And if you look back at your notes from last time, you were interested in a function that had a form like an exponential of say alpha. Let me do alpha, and then I was interested in t minus u plus maybe a beta t minus u times ru. If I'm interested in maybe in this process here, for two functions, of time, alpha and beta. So could we make this object here equal to mu? But if we want this thing, can we make this equal to the conditional expectation of E, I, psi, RT given FU? Well, we can do some things, but we take the left-hand side and evaluate it at U equal to T. Take the left-hand, the right-hand side, evaluate at U equal to T. Then the left-hand side becomes alpha at 0, E alpha 0 plus beta 0 RT. This is now the same as what's on the right-hand side. This is E, I, the coefficient zeta times RT. So what should be alpha 0 and what should be beta 0?
So alpha 0 is 0 and beta 0 is I psi.
Okay. And then for u less than t and bigger than 0, you need the martingale property. You need E alpha t minus u plus beta t minus u u to be a martingale. Okay, so we apply E2. So we're going to end up doing 2 exercises on E2 tonight. That was not the plan, but we apply E2. So we need derivatives. So the first thing we need is a derivative with respect to, say, x of this mess up here, e to the alpha t minus u plus beta t minus u, and then times x. Right. We need a derivative. What is this derivative? This is beta t minus u, and then the same thing, e to the alpha t minus u plus beta t minus u x. We also need the double derivative because there is Brownian motion inside R, so we need a double derivative. So we need a second derivative. The same function, right? There's nothing random about this function, right? This is just a function of current time u and the variable x. So we need the double derivative. Okay, but we already have the first derivative, so we just need to compute another derivative with respect to x on the right-hand side here. So this is not too bad. I'll get another beta down. I'm going to get a beta squared. E to the alpha t minus u plus beta t minus u times x. And now I also have time in here, so I need a derivative with respect to time. Current time is u here, right? Current time is u. So I need a derivative with respect to u. This function e alpha t minus u plus beta t minus u times x. So what do I get now? Take a derivative with respect to u. It's an exponential. I'm going to get the exponential function back. And so now we need to be a little bit careful about minuses. So we're going to get the derivative with respect to u, get the exponential, then I get alpha prime with a minus sign in front, t minus u. And then the same thing for the beta function, there's going to be another minus beta prime t minus u times x. Those are all my derivatives, and now I can apply Ito. Apply Ito. The dynamics of this process up here, e to the alpha t minus u plus beta t minus u ru. What are those dynamics? Well, Ito's lemma says take the first derivative. So there's all this mess here. I'll put this object here outside. And I have my RU. So that goes outside. And then what I have inside will be beta t minus u dru. So that was the first one. Then the next one is the second order derivative. I need the second order derivative. I need the second derivative. So this is the beta squared. I need 1/2 beta squared t minus u. And then I need the credit gradation of r. And then finally, I need the time derivative. Time derivative is this guy. So it's going to be minus, so alpha prime t minus u. Put in minus outside, so I get plus. And then this is my ru du. So now we're going to insert, we're going to use that dru was equal to a minus b ru du plus sigma square root ru dbu. Right, that's going to go in here. And the credit gradation is this guy over here. Credit gradation, I have drift, I have volatility. Drift does not contribute to the credit gradation, only volatility. This is going to be sigma squared ru du. Okay, so all the magic happened here. This is Ito. All the magic happened right there. So now what we do is, this is a martingale. I want this to be a martingale, so we're going to collect. We're going to collect dt term, du terms, and match them to 0 to get the martingale. So let's do that. So inside dr, I'll find there's some drift. So I have 0 needs to be beta t minus u times a minus b ru. That was something in there. Plus I have, that would be beta t minus u squared. And then the credit gradation of r, that was the one we computed down here. This was sigma squared ru. And then finally, the time derivative over here, this will be minus alpha prime t minus u minus beta prime t minus u IU. So we need to be able to solve this thing. Quite similar to what we had last time. What we're going to do now is we're going to collect RU terms. RU terms, and I'll match them up to 0. So I'll have here RU, there's a RU term here. This is going to be minus B beta T minus U. That took care of this term. I'll have a half beta T minus U squared, sigma squared. Took care of that term. And then I'll have my minus a beta over here. Beta prime T minus U. Took care of that term. And then we're going to collect remaining terms. But I want everything to be 0, so I'll match up the remaining terms. This will be beta A times beta T minus U. That was this term. And then over here I have alpha prime minus alpha prime of T minus U. So now the question is, we have our we have a system now of coupled ODEs. Can we solve them? So we have the system. We have the system that says beta prime of say S is equal to 1/2 beta of S squared sigma squared minus B beta of S. I know at time 0, what was the initial condition? This was I zeta. This was one equation. The other equation was this one. I'll have that alpha prime of S is equal to A beta of S. The initial condition was 0. So then the question is, can we solve these equations? Well, as before, if you know what beta is, it's not hard to get alpha. Right? So given beta, you get alpha by integrating. You're going to get that alpha of S is equal to the initial point plus the integral alpha prime. I think we're running out of letters here. U du. So alpha 0 was 0. Alpha prime was a beta. Yes, we have a U here. This is a U. So if you know what beta is, you get alpha by integrating. And if you look at the equation for beta, the ODE for beta does not involve alpha. So the question is, do you guys know how to solve an ODE that has this form?
Which form?
The one with the arrow. You see, it's different from the ones we just had.
Is it because there's a square term?
Yeah, there's a square term, right? This term here, this is trouble. Is not. It's not linear. So has anybody seen an ODE of this form here before?
I remember there was some method called integrating factor, but I'm not sure if it's relevant for this one.
So this equation here is actually quite famous. It has a name. It's called a Riccati equation. I always forget. It's either with 2 T's and 1 C, or it's with 2 C's and 1 T. So it could be when you Google it, you should look up. No, this doesn't look right. No, this doesn't look right. It's spelled like this. Riccati ODEs. And there's a closed form solution. So I think this is where I want to stop. I'm not going to write down and start working with these Riccati equations. If you are interested, look up what they are. There is a closed form solution for a Riccati equation. And so as soon as you have that, then you're done. You're done. You will have an expression for your M0. And then the question is, and of course, when you get your beta, you go one step back, integrate to get alpha. Okay, so then you have alpha and beta, and then you go back, and then you get M0. How would you get your M0? Well, as soon as you have this thing, your M0 is going to be, as soon as you have this thing, your M0 is going to be e to the alpha t plus beta t r0. And this is the thing that you were hunting. This is the thing that will give you the expectation of e I t ei psi rt. So as soon as you get what alpha and beta are, then you'll get the characteristic function for rt. And if you know what the characteristic function for rt is, then you know what the distribution is of rt. Any questions or comments on this part? It's a bit of a detour. We ended up using Newton's lemma one more time, and it allowed us to derive the ODEs that will characterize the characteristic function for RT, and thereby telling us what the distribution of RT is. For those of you that want to go through with this, you should end up proving that RT is a chi-squared distributed random variable. When you go through and actually work out what the solution is to this Riccati equation up here, and then you integrate with alpha, then you should recognize this expression over here as the characteristic function for a chi-squared distributed random variable. And the chi-square distribution has exactly this problem, that if you were to compute the moment generating function for the chi-squared, this is potentially plus infinity. Chi-squared distributed random variables do not have finite moment generating function for all t. Are there any questions or comments on this part? Good night, guys. Are there any questions or comments on what we've been doing now for the last hour? Are there some of the parts you want me to go over again? Now is a good time to say so.
Just wanted to ask about the when we say we apply Ito,
Yeah.
right? What's the general thing we're applying again? Just having a little trouble recognizing.
Where did I write it? Where we apply Ito, so I wrote it here, right? So to figure out whether or not this is a martingale, I need to compute the dynamics. So I apply Ito, so I should be more specific here, to compute d of e to the alpha t minus u plus beta t minus u ru. And so what we're going to be able to do is, what Ito's lemma will tell you is that this stochastic process, you'll be able to write this as something du plus something dbu. And what Ito's lemma tells you is what to put here and what to put here.
Got it. Okay.
Yeah. So we apply Ito to compute the dynamics of this stochastic process. This stochastic process is what I want to be a martingale. That's the goal, right? We know what the value is going to end up being. So if I tell you what if I tell you I have a martingale and I tell you what the terminal value is of it, then you can get all the previous values by conditioning, right? So it's sufficient to know that you have a what the terminal condition is and that you have a martingale structure.
Gotcha. Will it be RU? DRU?
Yeah, so you can so you can also write this here as, because DRU
is the Brownian motion.
Can be, you can write DRU as DU plus DBU. Because DRU had the form B, no, what was it? A minus B RU DU plus sigma root RU DBU. So you can also, instead of DU, you could write DRU here.
Okay.
DRU can be written as something DU plus something DBU. But to check for the martingale property, then you need to have a Brownian motion here. Because it's the Brownian motion that will give you the martingale, right? So if you can make sure that this term here is actually equal to 0, then you know that the stochastic process in question is a martingale. So whatever comes out of Ito's lemma, you'll get a bunch of terms in here in the drift. You get a bunch of terms in the drift, and if you can make sure that they match up, they add up to 0, well, then you're done. Then you have the martingale. And that's exactly what we did on the next slide. You computed all the du terms. Right, so here are all the terms that come out of Ito's lemma. There are a bunch of du's, dru, correct variation, but when you substitute in what dru is, and when you substitute in what the correct variation is, you get something that has just du and dpu. And then you collect all the du terms, and you match them to 0, and this will give you the martingale property, because what's going to be left is, if you carry through, page 9. So what remains is that if I look at D of this object, like what remains when we're done with all this, we will have that thing out there, e to the alpha t minus u beta t minus u ru, and then there'll be that term. And then inside here, there'll be that volatility term. This will be sigma root ru dbu. Like, so remember, this is nothing else than a shorthand notation for something that is much longer. This is the same thing as saying e to the alpha t minus u plus b t minus u ru. This is the same thing as the initial value. Okay, so now we take u to be 0. This is e to the alpha t plus beta t 0 plus, and then the stochastic integral from 0 to u. And then you write this mess up here. Alpha, say t minus s plus beta t minus s rs beta t minus s sigma root rs dbs. And so what we needed was this thing here on the right hand side. If I apply everything here for u equal to t, then what's on the left hand side? This becomes alpha of 0 plus beta of 0 times RT. So that becomes equal to everything again, but now with a u being t. T minus s. It's a lot of writing, but so now we have this formula, but now on the left-hand side, we knew what alpha 0 and beta 0 were. Alpha 0 was, what was alpha 0?
It was 0, and then
this was,
I saw, yeah.
So you see now, if I take expectation of the left-hand side, I'm going to get e to the I psi RT, and I take expectation of the right-hand side. This is a martingale. So the expectation is equal to 0. And I get that this is e to the alpha t beta t 0. So I get the characteristic function. Provided you can tell me what alpha and beta are, you get the characteristic function.
And it's going to be chi-squared after you do.
Yeah, well, you have to figure out what they are, right?
Yeah, yeah. Because there's no RT term, there's no randomness, and that's why you can just take the E out of the expectation.
Yeah, this is the initial value, right? This is just a constant.
Okay, so there's no, okay, gotcha. There's no randomness because there's no RT.
There's no
RT term.
right? Alpha and beta are just these deterministic functions that are given as solutions to a coupled set of ODEs.
Gotcha. Okay.
The randomness is over here, right? Because there's an R here, that's random. There's an R here, that's random, and then we integrate with respect to Brownian motion. So there's lots of randomness in this term, but it has the martingale structure. So that means when you take the expectation, it drops out.
Okay.
There's the martingale, so it has 0 expectation. So we're running out of time. I'm getting the impression that maybe not all of you have seen these ODEs so much, in particular these Riccati equations. There's one thing I wanted to show you guys. Maybe we should talk just a little bit about this here in the end instead of doing more new material. So just so what would happen? What would happen? So what would happen if instead we want this expectation? The moment generating function. How would you adjust the previous argument? And what would happen here? Any guesses on how we should adjust the previous argument? Well, the only place this I psi came in was when we prescribed what beta 0 would be. So if we wanted to adjust what we just did to the case where there's no I here, what would we put beta to be?
Just psi.
Just psi, right? So now let's have a closer look. So let's have a look at that Riccati equation one more time. Let's have a look at this Riccati equation. So we're facing beta prime of S is equal to 1/2 beta S squared sigma squared minus B beta S, right? And then we have the initial condition. This is psi. So what is the problem with this equation here? So let's simplify. Let's simplify by setting this guy here equal to 0. So now I'll have beta prime of S needs to be 1/2 beta squared times sigma squared. And I want it to be psi at 0. Let's try to solve this. So again, let's guess the solution. Let's guess that beta S is equal to psi divided by I think it's 1 minus 1/2 sigma squared I think there's a psi in here too, and then S. Okay, can anybody try to figure out what is this correct here? If I compute the derivative, what on earth do I get? Does it solve this equation here? Let's test the terminal condition at least. When I take S to be 0, does the form work? Well, if S is equal to 0, I'm just going to get psi divided by 1. That's going to give me psi. And then let's compute the derivative. If I look at beta prime S, so I need to compute the derivative of a composed function. The derivative of a composed function, this is doing what? What is beta prime here? This is, let me do a little calculation over here in the corner. If I compute the derivative with respect to x of 1 over 1 minus x, this is also equal to the derivative of 1 minus x to the minus 1. Let's see if I can figure this out. This is going to give me a minus, and then 1 minus x to the minus 2 times, and then I need the derivative of what comes inside, so I'm going to get a plus. Does that look right? So when I compute the derivative over here, I'll get 1 over the same mess. Oh, there should be a constant here, but I have a coefficient k here. So then I'll get a k outside. So this is 1 over 1 minus xk. So I have a k here. I need to multiply then with minus k, so I'm going to get k. Okay. So the derivative is whatever I had, psi s, and then I need to square it, times, and then I need to multiply onto the coefficient 1/2 sigma squared 1/2 sigma squared times psi. Does that look like what we have up here? Does it look like what we have up here? What is my beta squared? This is psi squared divided by 1 minus 1 over 2 alpha squared psi s.
Wait,
missing
shouldn't the denominator be squared too?
s squared too, yeah. Looks like I'm missing a psi somewhere. Where am I missing? Where's the psi missing from?
Is it from maybe when we did the change?
Let's simplify by setting b equal to 1 and setting psi equal to 1. Then it works because it doesn't matter whether I have a 1 or 1 squared here. The point I'm trying to get at, if you look at then what I'll have downstairs, watch out for the downstairs one. So if I put psi equal to 1, I will have I'll have that beta of s is equal to I'll have that beta of s is equal to 1 divided by 1 minus 1/2 sigma squared s. And so what happens down here when what happens when s get big?
Goes to 0.
In particular, what happens when s is equal to what happens when I have 1/2 sigma squared s is equal to 1? So what happens when s is equal to 1 divided by 1/2 sigma squared? What happens to this guy up here?
It gets close to infinity.
Yeah, explodes. Then beta of x explodes. And then it doesn't, so then it can't solve. It can't solve this equation, beta prime of s equals 1/2 beta s squared sigma squared. And now the initial condition, because I can't figure out how to compute the derivative, so the initial condition is just 1. It can't solve this equation here for s bigger than or equal to 2 divided by sigma squared. So this is just something to look out for. When this nonlinearity comes over here, this ODE is not going to have a solution for all s. So if you've not seen these nonlinear ODEs before, this is like this is a problem with them because they only have finite solutions, perhaps on bounded intervals. So even though this looks pretty innocent, it's not, because you can only have s going up to this particular constant. After there is no solution and it explodes. Okay, I think this is plenty for tonight. So Kisano's theorem has been postponed until after Thanksgiving. It's time to call it quits. Are there any last minute questions here? Okay, if there are no last minute questions, enjoy a few days off, guys, and
Happy Thanksgiving.
same to you. And yeah, it's going to be a bit different this year, but try to make the best of it, of course. And otherwise, I will see you guys on Tuesday next week. Take care, guys.